Okay, this is our last lecture of this year. Before I go into, so I'll do a short review of things that you have to remember for the exam and things that we've seen throughout the semester. Hopefully, this will give, it will just allow you to have a bigger picture view of the class when you start studying. I had a number of questions about this 4 here from last lecture. It shouldn't be there. It's just because in my notes I called u half of u1 minus u2. So here I didn't define this u, and so it's still u2 minus u1 squared. The 4 should not be there. I will post a more complete version of the way you solve. Once you put all of the system into equations. Remember, we have 3 algebraic equations. Those 2 that come from the kinematic boundary condition apply both to the fluid layer on top at the interface and the fluid layer on the bottom at the interface, and as well as the normal stress boundary condition. You have 3 algebraic equations, and you solve them to get a relationship between your wave number, which relates to the inverse of the wavelength, and your wave speed. Right. So it takes a little bit of algebra, so I didn't do it in class, but I'll post a PDF that develops the notes. Or alternatively, you can look in the book, right? Or the derivation is also in the book. So if it's easier for you, you can just look it up in the book. Okay, and so today what we'll do is review, try at least to review the whole of the class. And so for that, I'll just go refer you back to the roadmap that we developed during the first class, and write down most of the equations which you need to remember, or at least their names. So I'm not saying this is extensive, but it will cover most of the things that you have to remember. Of course, I cannot summarize in 2 hours what we did in a whole semester. So there will be blanks, but hopefully we'll give you a broad picture on how to approach the different problems. So if you remember from our roadmap, we started saying that we needed to derive the governing laws for fluids. And so there are 2 broad conservation principles, or physical principles, from which everything in fluid dynamics originates. And that is mass conservation, and that is Newton's second law. Just the fact that forces are what changes the momentum of mass of a certain material. So those are the 2 broad things. Hopefully, I think I hammered down that during the course of the class, but you should be really very familiar with this. If in any problem you haven't balanced your mass and haven't made a statement of momentum equation, whether it's in the integral form or at the differential form, then most likely you're missing something in the system. So it could be that you're just turning around and not able to solve the problem. So those 2 broad principles of mass conservation. Let me write that here. And Newton's second law. And of course, the 2 quantities this relates to, mass conservation has to do with mass, and Newton's second law has to do with momentum. If you have a system with no externally applied force, remember, you're not applying any force, the momentum is conserved, and you have conservation of momentum. If you have external forces, then your change of momentum is equal to the sum of all of the external forces. So the way we started was to look at a control volume. So we started with the integral form of of mass conservation and Newton's second law. So remember, control volumes is you just define a macroscopic volume of mass of material. Now, most of the control volumes we've looked at were control volumes that were fixed in time, which meant that we had flow coming in and out. We can also define a control volume. In some problems, we define a control volume which was following the same amount of mass. Right? But usually we picked fixed control volumes, so they are open they are open systems in the thermodynamic sense. You have mass coming in and mass coming out. So we call control volume CS, CVCS. Remember that the normal, when you define a control volume, in everything we did, we always define the normal as pointing outwards of the control volume. That's a convention. And so what we derive from there is the integral form of the governing equations. So when you write everything on the control volume, you're essentially at the integral level. Integral form of the governing equations. This is where we started. Now, for the mass conservation, the integral form takes the following form. So you consider all of the mass, which is inside of your control volume. The mass inside of the control volume is the volume integral of the density dV. Right? You integrated all of the pieces of mass inside of your control volume. And mass conservation simply states that if this mass changes, it has to be because there was a difference between the mass flowing in and the mass flowing out. Right? Or there was a non-zero net flow outside, coming out of the system. So the volumetric flow rate is the double integral over your control surface of u dot nds. U dot nds here represents the volumetric flow rate, and so if you want the mass flow rate, then you just multiply by the density. This is your volumetric. This is your mass flow rate coming out of your control volume, and if you do a simple balance and reasoning, you realize that there has to be a minus sign here. So that's mass conservation at the integral level, and for the momentum equation, well, you have the same. So you're writing your momentum inside of your control volume. So it's just the volume integral of you're just summing all of the pieces of momentum inside of your control volume. This is the entire momentum inside of your control volume. So if you have changes in this control volume, in the momentum in your control volume, so this is the change in momentum, that's the left-hand side in Newton's second law, then you have to have non-zero, this is non-zero, then you have to have external forces. So we wrote those. So you have surface forces. So this is plus all of the surface forces, and we saw, this is from the work of Cauchy, that the surface forces you can write as a matrix, which is your stress tensor times the normal vector. And you integrate this over ds. So the matrix, your stress tensor times the normal vector here, this is your stress vector. That's the piece of force which is applied on the small surface ds, and you integrate over the entire control surface. That's the forces which is applied at the surface of your control volume, and you have to add all of the forces which might apply to the bulk of the inside of the control volume, and the only force we discussed which is applied in the bulk was gravity. Now, in some cases, you may have in some fluids, you may have other forces. If your fluid is charged, for instance, and you impose an electric field, then you might have a body force, which is a Coulomb force, because you have charges inside of your fluid. Or if your fluid has, Anyway, so this is exactly Newton's second law, except we have an open system. So another reason why the momentum inside of the control volume may change is because you have more momentum coming in than momentum coming out. So you have a non-zero net momentum flux coming out of your control volume. So you have to add the same term, which corresponds to this term here in the mass conservation equation. So you take the volumetric flow rate. So this is still u dot n ds, and you integrate over the entire control surface. Right, so this is here again your volumetric flow rate coming out, but now you're not interested in how much mass came out, you're interested in how much momentum came out. So you have to multiply your volumetric flow rate by the momentum. So this is rho u. Okay, and so this here is the integral form of the momentum equation. Now let me put a few labels here, there are a few concepts which you should go back to. This T here is the stress tensor, and we discussed certain properties of the stress tensor, namely the fact that it has to be symmetric. That's from balance of angular momentum. So there are certain things here which I'm not developing, but we had a whole lecture on the stress tensor, so go back to the stress tensor. Okay, so these are the first equations we derived. And you always go back to these equations if you're solving the problem at the control volume. Okay. Now here I'm just going to stop and make one short comment about an error which was very recurrent in your midterm. So I'm going to go a few pages down because I don't want that to block the flow of the lecture. And I'll take a simple example. So let's say that here you have a wall, and say you are injecting fluid. That's there was a homework problem where we had a pump, which was an entrainment pump, right? So this is essentially what you could think of. So say you have this inlet here, and you have flow flowing here at velocity u. Say this is A1, U1, and say you have a tiny opening here, maybe it's a bit smaller. Everything which is coming in here is coming out there. Let's say the opening here is A2, right? And say the question is, what is the force exerted by the wall onto that like bended pipe, like this nozzle? This is here a nozzle. That could be the question, or it might not be directly asked, but you realize that you actually need to compute that, either because in your control volume you cut through the surface, or for any other reasons. It doesn't matter for this illustration. In any case, you all know how to balance your mass. So this you know how to do. Most of the time you write the equations right. In that case, you write dt integral of rho dv is equal to minus rho u dot n ds. If you know what this is going to be in an exam, you don't have to rewrite that. Right? If I know you saw where it's coming from, you don't always to rewrite everything. I'll do it here just for clarity. So then you say, okay, I have a steady state, right? And then therefore this is essentially roughly, this is equal to the summing everything which is coming out, or you can say you can add the signs at this point. It doesn't really matter. If I'm writing it as this, then the flux coming out is a negative sign. So here I have rho A1 U1 minus rho A2 U2. And that has to be equal to 0, right? And then you write that U2, so the rho, if it's a compressible, is constant, and you write that U2 is equal to A1 divided by A2 times U1. And this is fine because this here is like mass is a scalar quantity. Right? This is a single equation. The problem is that you do the same for momentum. Many of you did the same thing for momentum. Momentum is a vector. It has two directions. So when you write conservation of momentum, right, you have to write it on, either you write it in full vector form, but if in the end you get a scalar, that means that somehow you project it either in the x direction or in the y direction. What I saw many of you do is do something very similar, where then you say, well, this is the momentum coming in, and this is the momentum coming out. But that doesn't work. Right? So when you write conservation of, or when you write Newton's second law, you have to write all of the pieces. So this is rho u dv equals to minus, what is that? Rho u dot n ds plus stresses plus the volumetric, the bulk forces. Now here, at this point, here, sometimes you can get away with the mass without really properly defining your control volume. In that case, you really want to properly define your control volume. So let me show you which control volume I would pick. Right? I would pick this control volume here. Right? You can also pick a control volume which is like that, but then it's a bit more bended, and you want to make sure that you actually cut through the material at this point. Right? And let me show you why. So then you have a steady state, so this here is equal to 0. Right? And then you have here, that here is a vector identity. Right? It's not a random thing. So in this inlet, you have a momentum flux in the y direction through the inlet, and through the outlet, you have a momentum flux in the x direction. Right? So actually, you know what's going to happen. In order to bend the flow towards this direction, you're going to have a higher pressure here on the outside. So the pipe, the nozzle, essentially has to exert a force onto the flow to bend it in this direction, and that will result actually into a net force onto the nozzle here. There is an extensional stress inside of the nozzle. I mean, the flow, because you're bending it, is pushing. If you cut through the nozzle, your nozzle will leave. It's not going to stay there. So there's stress in there. When you cut through, there's stress, and there's actually stress in both directions. And you'll see it here. So either you rewrite all of the equations in that form, which is sometimes a bit complicated, or you actually already know what's coming out. So either way is fine. I'm just going to do it fully here so that you see where it's coming from. Now, first of all, when you integrate along this is along my control surface, this is also along my control surface, and this is control volume. This is equal to 0, we're neglecting body forces, so we only have to worry about those two terms here. Now, when I integrate along my control surface, I haven't said anything, but you might see that everywhere I'm at atmospheric pressure outside. Right? So on my outer boundary here, I'm not going to have a big contribution of pressure anywhere here. I might have a contribution of pressure here, of course. I haven't said anything about that, and for this you would have to use Bernoulli. But at least on the outside part of my control volume, so let me split this control surface into different parts. So my integral is going to include all of that, right? And also all of this. Right? When you integrate around the entire control surface, you have to integrate around the entire control surface. Yeah? So this is my control volume. My control surface is the boundary. So I'm going to integrate throughout this whole thing here. Actually, I have 3 bits. Let me also add that you have this little bit here where you cut through the material. Right? And you have to distinguish all of these. So when you look at this integral here, you only have a non-zero volumetric flow rate on the red part. You see that? So this is why in this integral only those little sections are going to show, because elsewhere there is no volumetric flow rate. Right? I'm assuming here the flow is at rest everywhere else. Right? Is that clear? There's no volumetric flow rate, but it doesn't mean that you didn't integrate over those areas. You did integrate over those areas, except there is no volumetric flow rate because there is no flow motion. Huh? So in the end, the only terms you're going to have left here is let me call this the inlet, and this is the outlet. So you have only 2 bits of this integral along the inlet and the outlet, and along the inlet what you get is, so let's say I'm integrating over the inlet, so I have minus rho, and over the inlet my velocity is in the y direction, so u is 0 u1, right? And what is this? How do I get rid of that? Okay, and u dot n, so my n vector is the normal vector pointing outwards, so it's in this direction, so it's minus y. So I have 0 u1 dot 0 minus 1 ds. So in the end, this here gives me rho u1 squared times a1, but it has a direction. It's on y. Yeah? Is that clear? This here is a dot product, yeah? So this here is equal to minus u1. So I end up having the vector, well, let me just write in vector form. I think this is easier. So then I end up having rho 0 minus u1 squared a1. This is what I get. And when I integrate over the outlet, so plus, no, minus, because I have this minus sign. I still have this minus sign here, eh? This minus sign. So I have minus the double integral over the outlet of rho. Now when I'm looking over this outlet, I do have a volumetric flow rate, but now the velocity is in the x direction. And so u2 is in the x direction, so I have u2 0, and here I have u dot n, u2 0 dot my normal vector. What is my normal vector? 1 0. Huh? My normal vector here is 1 0 ds. So I get here minus rho u2 squared a2 0. Okay, so that's what I get. What the mistake that many of you did was just to have those two on the same line, because you applied conservation of momentum the same way you apply conservation of mass. But that's only going to be true if mass comes in and out of the same. You know, of course, you guys might be used to a configuration like this, right? Like if the flow is always just in one direction, then it looks the same. But it's fundamentally different. Momentum is a vector, mass is a scalar. Is that clear? So beware of that. Right? Many of you made this mistake in the exam. So always remember, when you apply conservation of momentum, even in the control volume level, it's a vector. Right? So you have to keep track of that. Now let me just briefly tell you what the effect would be on this. So here, when I integrate that, you have to integrate all of your stress tensor over the entire control surface. Now, if I'm integrating along those two surfaces here, right? Here I only have PA, atmospheric pressure, pushing, and here I only have atmospheric pressure pushing in this direction. So it is clear that in the x component, on the x direction, the pressure is not going to add anything, right? Now, so here when you integrate this has no component in the x direction and has no component in the y direction when you integrate over those two bits here. Now it's a bit more tricky when you integrate over those two bits here, so this bit here and that bit here. So here on top it's the same, I only have PA pushing here. On the bottom I have atmospheric pressure. You know, let's say my control volume was just above the surface. I would also have atmospheric pressure pushing here and there on this part. Now on the red part, what do I have? Now you're inside of the pipe, so you have to have the pressure which is inside of the pipe, inside of the nozzle. And that pressure might be different than atmospheric pressure. How would you know what this pressure is? Bernoulli. Right? If the flow is invisive, then you can follow a streamline from here to here. You know what the velocity is there, and you know what the velocity is there from mass conservation, so you know the ratio of pressure, how the pressure has changed. So here you would have to add a little bit of this pressure, so it would look like on this entire surface here the pressure was cancelled by the pressure on top of here, right? But then on that little bit you have P acting here and you have PA acting there, so you would have the P inside minus the P outside on my control volume, over this little surface. So you would have this bit And then there's another bit which you have to take into account, and this is what happens exactly where you cut the material, right? Where you cut through the material, formally your stress tensor now is no longer the hydrodynamic stress tensor. And remember, the hydrodynamic stress tensor is minus pi plus 2 mu e. Now you're cutting through a material. If the material is elastic, then you would have the stress tensor that you have inside of a solid. In particular, if you were looking in the normal direction, right? So if I'm looking now in this x direction, and you cut through the material, then you're cutting through your normal stress, and in the material, you know, the normal stress would be equal to your Young's modulus times your extensional strain in the x direction. At this point, you know, in fluids, we don't really look into that. But when you cut through this material, right, and you integrate over the surface of your nozzle, like the material surface of your nozzle, then when you integrate that, essentially what you get is the force which the ground, or which one part of the nozzle which you cut, is exerting on the other one. And you see here that this would have two components, one in the y direction and one in the x direction. Yeah? That's just to really highlight conservation of momentum. The momentum equation is a vector identity, so you always have two components. If the flow is flowing in two different components, then you'll have two components. You always have to keep track of both. Okay? Good. So let's go back to our review. So this is where we were. And so there are a number of problems which you can solve just at the integral level. The next step we took was to then generalize those equations. Just say essentially that we take all of these equations because they are true on any given control volume, any given control surface. If we just take all of the small control surface which are entirely included into the fluid or into any or into the solid, then it has to be true at the differential level, and we came up with the equivalent of those equations at the differential level. So we move to the differential level. And so that led to two equations. So the mass conservation written at the differential level is called the continuity equation. And you can write it as partial rho partial t plus u grad rho plus rho divergence of u is equal to 0. That's the continuity equation. We also discussed that actually this part here we can write as d rho dt, where this represents the material derivative. And remember, the material derivative is a way to represent with our more Eulerian-like coordinate system, is a way to represent how quantities change when you look at a piece of mass, at the material piece of mass, and follow it in time. Right? So it is a way of, when you're writing a conservation law, the most natural point of view is the Lagrangian point of view, where you follow a piece of mass. This is what you've been doing in high school. When you impose Newton's second law on an object which you throw, you impose it on a material piece. You follow that piece of material, which has a certain mass, certain properties, density, and everything, and you impose Newton's second law on this piece. If you're looking at a fluid, it's also most natural to impose the conservation laws on a piece of mass which you follow, except that the coordinate system then is very complicated. How do you represent every single moving point in a fluid? This is analytically impossible. So the way is to use the material derivative, which represents the time changes of a material element, so an element which follows the flow, but using our Eulerian coordinate system of independent variable x, y, z, and t. Yeah? Okay, so this is what we get when we look at the mass conservation equation. And when we look at Newton's second law, the momentum equation, we get to the momentum equation. Which is rho partial u over partial t, where u is the flow velocity field, u grad u is equal to minus, well, is equal at this point. We haven't said. Let me first. After what we discussed is the Cauchy momentum equation. So here we haven't distinguished whether we have a fluid, we have a continuum, but we haven't said what kind of continuum do we have. Do we have a solid, do we have a fluid? We haven't discussed it at this point. So here you get the divergence of your stress tensor plus the volumetric, the bulk forces. That's the first equation that we derived. So here this is all of our equation written for a continuum. And then we went more into what it means to be a fluid, and for that we discussed constitutive laws. And in particular we discussed constitutive relations, sorry. And for that, we discuss what it means for a fluid to be Newtonian. So here we briefly discussed non-Newtonian fluids, and then we discussed Newtonian fluids. And actually, everything we did later, we just looked at Newtonian fluids. We never looked at anything else but Newtonian fluids in detail. Newtonian fluids being fluids where your stress tensor is linear into your rate of strain tensor. Right. So go back to this lecture. It's important you understand the concepts associated with that. But that allowed us to derive a formula for the stress tensor, and write that the stress tensor inside of our fluid, our Newtonian fluid, is minus the pressure times I. Remember that here we discussed what the pressure represents. The pressure represents an isotropic stress which will always develop inside of the fluid when either the flow geometry or whatever the boundary condition tends to want to compress or extend the fluid. The only stress which can develop in a fluid in a static configuration, so when there is no motion, is an isotropic stress, and that is what the pressure is. So if you have water, you can impose, you can try to compress that water. Just think about a chamber and you have a piston and you push on it, and what will develop, and maybe there is no flow because there is no outlet for the fluid, then there will be stress inside of the fluid. But this only stress which can develop, you are in a static case, so nothing moves, is this isotropic stress, and that's what pressure is. Yeah? So minus Pi plus, and this is when we assume the flow to be Newtonian, 2 mu times E, where E is the rate of strain tensor. Now actually I jumped one thing, so let me just write that real quickly here. This is the rate of strain tensor. This is also a concept you have to go back to. E is the rate of strain tensor. It's equal to 1/2 times grad U plus the transpose of grad U. Right, rate of strain tensor. But we made two parallel assumptions. So for one, we discussed what a Newtonian fluid would be, and at the same time we assumed incompressibility. because you have to remember that the incompressibility condition slightly fed into this relationship. This is only true if you have an incompressible flow. If you have a compressible flow, then there is an additional term here which has to do with the bulk viscosity. Right? So if you want to get rid of the bulk viscosity, which is, this comes in when you have compressibility in the fluid. So for instance, in acoustics, if you're doing any acoustics, acoustic waves are waves that that are transported when you have compressibility in the air. Then you may have bulk viscosity come in. But in any of our applications, we never have bulk viscosity come in to play. And especially when you are incompressible, then formally, analytically, the bulk viscosity, the part of the stress tensor which is due to bulk viscosity disappears because there is a divergence of U in front. And so that led to the version of the Navier-Stokes equation which we use in this class. So let me write them down. Here, when we assume the flow to be incompressible, that means that we assume the density doesn't change. So d rho dt is equal to 0. This is the incompressibility condition, in which case the continuity equation reduces to just divergence of U equals to 0. So here with the incompressibility, we went to divergence of U equals to 0. This here you can call the continuity equation, or some people would call that the incompressibility condition. So this is continuity or incompressibility condition. And when you insert this expression for the stress tensor, then you get rho partial U partial T plus U grad U equals to minus grad P plus mu Laplacian of U plus your bulk forces. And I don't know why I keep writing this as a matrix. Okay? And these are the versions of the Navier-Stokes equation that we mostly use in our class. Now the reason why I'm reminding you of that is just for you to remember in which order we made those assumptions. So there are certain things that we did say about compressible flows, but we rapidly just limit ourselves to compressibility, so that you see the trail of assumption that we make. Okay, so these are the Navier-Stokes equation. So we started with that. Okay. Now there are a few immediate cases that we briefly discussed. Right. One case is a static case, right, which most of the time you call hydrostatic, because those are problems in water, but it doesn't have to be hydrostatic. But the hydrostatic case is the case when everything is static, meaning nothing moves, in which case the Navier-Stokes equation reduces to minus grad P plus your external forces is equal to 0. Right. So those are certain cases. For instance, when we looked at if you're looking at a glass of water on a rotating table and you are in the frame of reference rotating, then it's a hydrostatic problem because there is no motion. You have a solid body rotation, and this problem we were able to derive the shape of the interface. That's a hydrostatic problem, for example. Okay. Right. Another form of this equation that we derived from the momentum equation, we derived the equation for vorticity, the vorticity equation. Now, sometimes you do solve the vorticity equation, though it's a bit of an awkward equation to solve. Conceptually, the reason why we introduced the vorticity equation is just to give you a little bit of a feel for when can we assume flow to be incompressible. What happens to vorticity? Just to see that vorticity is a quantity which is both advected and diffused. And in all of the 2D problems that we looked at mostly 2D planar problems. we saw that there is no source term for vorticity, so we know that vorticity is only either advected or diffused. So those are also two things which, I'll put those in red, but two concepts which you should revisit, in terms of transport, and that is advection versus an advective process or a diffusive process. And I know, this class is not the only class where you've seen that, and you've seen that in your heat transfer problem a lot. So it's similar. Right? Those are concepts which come back, but which you want to revisit, and especially you want to revisit the scalings of all of these. Okay, and so in this whole section about our governing equation, the last thing which we discussed in detail were the boundary condition. Right? All of these equations that I'm writing, you're writing them always in the bulk of the fluid, and you're essentially writing that same PDE at every single point inside of the fluid. Right? If you have a vector field U and a pressure field P which satisfy this equation at every single point inside of the bulk, you have a solution to the Navier-Stokes equation. But of course, U depend on what you're doing at the boundary of your domain. In some cases, you're imposing a gradient of pressure. You may have different geometries. So the boundary conditions are, it's the same as when you're solving a simple ordinary differential equation. You need, if you're solving a one in time, an initial value problem, you need your initial value to solve the OD. The OD is not enough to have the solution. You need to know what happened initially. If you're solving a boundary value problem, you have, for instance, just the Laplace equation. So in a conduction problem, for instance, if there are no sources, you have that the Laplacian of the temperature is equal to 0. The Laplacian of the temperature, right? Well, if you want to know what the temperature field is, you need to know where the temperature was, or what the heat flux was, or something. You need to know something about what happens at the boundary. Right? So the solution to these equations are always depend on the boundary conditions. So we discussed boundary conditions, and those you have to master also. So we discuss boundary conditions. And so there are two kinds of boundary conditions on the velocity field, and boundary condition and stress boundary condition. Boundary condition on the velocity and stress boundary condition. And so you have to remember that, again, velocity and stress vectors or forces are vectors. So you have different directions, and the important directions are, when you have a boundary, the direction normal to the boundary and the direction tangential to the boundary, because they are different. So for the velocity field, you have a condition on the normal direction, on the normal component of the velocity. So that would be u dot n, and that is called the no penetration boundary condition. So you have to have continuity of the normal component of the velocity field. This is called the no penetration boundary condition. It is actually physically directly comes from mass conservation. So you impose that at any two boundaries. You have two emissive fluids, then you have to have a no penetration boundary condition. Or if the interface deforms, then that becomes a kinematic boundary condition. And at a solid wall, if the wall is not porous, so there is no air that can penetrate inside of the solid wall, then also you have a no penetration boundary condition, because you're simply stating that mass cannot leak out of your domain through a solid wall. So that's the no penetration boundary condition. And on the tangential component, that is more of a phenomenological law. It turns out that if you do measurement, this is close to being true. For a viscous fluid, and all fluids, besides a few exceptions, like superfluid helium, all fluids have viscosity. Then you have a no-slip boundary condition. And the slip boundary conditions simply state that you also have to have continuous tangential velocity. So if you're thinking about a fluid, it's sort of natural that you would have no jump in neither the normal or the tangential component of the velocity. You don't expect jumps in the velocity. Discontinuity. You don't expect the velocity here to be 1 and 1 angstrom underneath to be 0. You expect continuity of, in a continuum, you expect continuity of the velocity field, and so by extension, when you reach a solid interface, you expect continuity too. Now remember that later on we'll discuss what we assume when we assume inviscid flows and viscous flows, but if you assume the flow to be inviscid, so if you neglect the effect of viscosity, the only boundary condition you can impose on the velocity is the no penetration boundary condition. Right? Because you're assuming that there is no viscosity, therefore there's actually no physical mechanism inside of your model to satisfy the no-slip boundary condition. Even if you tried to satisfy the no-slip boundary condition, you couldn't analytically. Okay? And then the stress boundary condition is the same. You have the normal stress boundary condition. So let's think about a fluid-fluid interface, for instance. At a fluid-fluid interface, your normal stress boundary condition, you're just saying that the normal stress has to be constant. When we assume inviscid flows, then remember, that means that in my stress tensor here, if I assume my flow to be inviscid, I'm neglecting the effect of viscosity, so in my stress tensor, I only really consider the pressure term. Right? And so when you think about the normal stress boundary condition, you have to have continuity. You have to have essentially you have to balance your momentum again. Right? Your force have to be balanced. So if you have a fluid-fluid interface of two miscible flows, so there's no surface tension, then you're just saying that the pressure has to be continuous across that. The pressure has to be continuous. This is essentially what you're saying. This is what the normal stress boundary condition is. Now, if you do have an interface, like in the water-air interface, in the water-air interface or water-oil interface where the interface can carry some stress, then you're just writing that you have a jump in pressure, and that this jump of pressure corresponds to, is equal to gamma times the curvature. Right? So we discussed that at length. Just remember this diagram. If you have curvature in this direction, that means that the pressure underneath is higher than the pressure on top. Right? And that is because surface tension is a force which is in this direction. Right? So if you're thinking about an equilibrium, force equilibrium, and you're thinking about the pressure on top and the pressure underneath, in the positive direction I have the pressure underneath pushing, and in the negative direction I have the pressure on top, and I also have these little components of forces here due to the surface tension, so I know that the pressure underneath is larger than the pressure on top. But what you're writing is just a force equilibrium. Okay? This is the normal stress boundary condition. So for inviscid flows, mostly it's just related, it's a condition on the pressure. It's mostly related to the pressure. You also have a tangential stress boundary condition. Again, if you have a fluid-fluid interface, essentially what you're saying is, say there is no surface tension, there is no way that your interface carries any stress. So if you have two miscible fluids, for instance, then you're just saying that the tangential stress has to be continuous. Right? And the tangential stress can only be, just think about this, your stress tensor here, the tangential stress, you only have tangential stress in this component here, the one that has viscosity. This here is an isotropic stress. Right? So when you multiply, your tangential stress is your stress vector dotted on your tangential vector. Right? So this, if you do if you look at this component here, of course, the pressure term will not give you any contribution. Times N dotted on T is minus P on N, and N and T are normal, so this is equal to 0. And so you will never have any pressure in that tangential stress component, in that tangential stress boundary condition, sorry. So tangential stress boundary condition is, again, just continuity of tangential stress, unless there is a stress in your interface. And what we saw is when you have surface tension, if your surface tension is constant, then you never have, then your interface never carries tangential stress. Only if you have a gradient of surface tension, for instance, if there is a gradient of temperature, or if there is a gradient of concentration of any chemicals, whether it's alcohol or surfactant. Okay. The same observation as what we did for velocity boundary condition holds true for the stress boundary condition. For the stress boundary condition, if you assume the flow to be inviscid, then you can only impose the normal stress boundary condition, because again you have no mechanism to impose a tangential stress boundary condition. If your flow is inviscid, just realize that the whole viscous part of your stress tensor is not going to give you any contribution to a tangential stress, because you only have pressure essentially, right? Now, if you do have viscosity at a water-oil interface, for instance, and say the flow is unidirectional, so you know that viscosity is going to be important, then you have, of course, to match your tangential stress at the boundary. And the tangential stress boundary condition in that case would be just if you have a water layer on the bottom, mu d water partial du dy, and this is in the water layer, has to be equal to mu oil du dy in the oil layer. This is in the oil, this is in the water. It will be something like that. You have different viscosities. Okay? Okay, so this is a review of I think, most of the first semester, and then we'll review the rest of the first quarter, and then we'll review the second quarter after the break.